Nash equilibrium. In this case, no. This game does not have a strict mixed strategy Nash equilibrium. Any questions about this? I know it reaches 240, I think 250 is the moment of the class, so you guys can choose for it. Now, understand that. We're about to get to the end of the class, and we still have to talk about the Nash theorem. Are there any questions? No. The definition that we have for Nash equilibrium is a situation that no one has incentive to deviate or to act differently unilaterally. Okay, so a way to see this in this strategy is that they're finding a Q that maximizes their field. So that's true for all mixed strategies, and actually it's true for pure strategy. They're maximizing their field. So I go there and pick first order condition to figure out this Q. If it happens that there is no, the first order condition is always bigger than 0, it's going to mean that there is a dominant structure. Okay, but I do this for every possible game. When this occurs, for every possible Q, so then it's randomizing, your sign prefers to go this. It's a little bit of a circular point here. We know already the best option is to compress. We figured out this by looking at the data. We were checking to see if there was another another option that would be good, another possible equilibrium. And we figured out that there is not. It's just like, in this game, you could use this equation and say there is no mixed strategy Nash equilibrium because there's a dominant structure for that. So for a game, if it's correct, it's correct. I'm just doing this to show that in this case here, we have a game where there is no strict mixed strategy Nash equilibrium. You don't have to do this to find it. Any other question? Okay. So perhaps you're now thinking, fine, you showed us one example where there is a mixed strategy Nash equilibrium. There's only one strict mixed strategy Nash equilibrium. You showed an example where there are two pure strategy Nash equilibrium and one mixed strategy Nash equilibrium. And you showed an example where there is one pure strategy Nash equilibrium and no strict mixed strategy Nash equilibrium. What is the general rule? Right? Can we always say there is an equilibrium? Do you know how many equilibrium are there? This was something that was puzzling the mathematicians for a while. then in 1952, John Nash, a beautiful mind, also known as Russell, proved the theorem that every finite game has at least one equilibrium mixed strategies. Nash did this contribution for economics. He has a few other contributions in bargaining, and that's it. And most of his works in mathematics. He has this contribution which is a pretty sound result. People were looking for it for a long time. He also has another way, which is Nash bargaining, how people solve a bargaining problem, which he published, was a very important result, and he published as his undergraduate thesis. And I think that was it. And in 1992, he won the Nobel Prize in economics. It's a pretty important result, and pretty simple. When we mean mixed strategies here, we mean mixed strategies could be pure strategies or strict mixed strategies. Pure structures. This was a pretty solid result. Any questions here? So we have today seen a few more rigorous definition of what is a mixed strategy, what does Nash equilibrium imply for mixed strategies. We saw a few different games and some results, and we figured out with the Nash theorem that says that every finite game has an equilibrium in mixed strategy. In the next class, we're going to talk about sequential games. Games where I will slow what the other player does before I decide what I do. And the concept of this theorem still holds there, but you're going to need some other theorems to figure out, because some very easy. Okay, I'll see you guys. Questions?